Um, well, today has been an absolute pleasure to be able to have so many amazing folks give talks, so many amazing researchers, science communication communicators. But I've been looking forward to this talk with Dr. Mike Rich from UCLA. Mike and I go way, way, way back. I was a postdoc, got my PhD at Santa Cruz, and then I was a postdoc at UCI for just 1 year. And things didn't go well. I'm not going to dwell on that too much, but Mike got wind of that and thought, I want to give this guy a chance. I want to see if I can help him out. So, the reason I'm here today and still talking to you about exoplanets and science and communication is all due to Mike here, Mike Rich. So, I have him to thank for saving the thing I'm probably one of the things I'm most passionate about. I love music as well, but space and astronomy has always fascinated me. And Mike provided me the environment to be able to go do some work, to be go do observations in Chile and Hawaii, be part of this wonderful Brava survey.
Oh yes, I remember you took and reduced the data.
Reduced so much data and got so much data
where
down in
we
Chile.
mapped the velocities of the galactic bulge.
So Mike has led some amazing research projects that others just didn't think of, thinking, well, let's use the 2-mass survey to go find these red giants down in the bulge of the galaxy. Kinematic survey that had never been done that people are still using today. If you go look at big space projects, Galax, Cosmos, you go across the board, whose name is there? Mike Rich's name is there, involved in pretty much every major astrophysical project that's been going on. And there's a reason for that. He's brilliant. So thank you so much for being with us today, Mike. And he's going to talk about the astronomical century. So ladies and gentlemen, let's all welcome Dr. Mike Rich.
Thank you, David. Thank you. I would say that David also saved the bulge radial velocity assay project too. And so it was a mutual thing. He's fantastic. Another career that I saved for the story for another time was that of Neil deGrasse Tyson, who was my graduate student at Columbia University. In 1991, he did his thesis. So that's another story for another time. What I'm going to talk about today is a remarkable age of discovery. You may have heard of the term the age of discovery. And, when people were in the Renaissance or the age of discovery, they didn't walk around saying, do you realize we're in the Renaissance, or we're in the age of, no. From the period 1920 to 2021, in 100 years, humankind discovered the contours of the universe, understood why the stars shine, which we did not know before, the composition of the universe, the age of the universe, the origin of galaxies from the Big Bang to the present, the Big Bang itself. We landed on the moon and we explored the solar system with probes that took high-resolution images of all of the important bodies of the solar system, including Pluto, which we canceled the grand tour because we had much more important things to do, which was to continue fighting the Vietnam War. Sadly, this country is retreating very dramatically from its age of discovery, which it led in the world in the astronomical century. Hopefully, we can turn the tide back and refocus the country in the support of scientific research, which is crucial for maintaining individual health, the primacy of our country relative to countries that would do us harm, and also the health of the planet. Scientific research is important for all of these things. So, but anyway, I will get back to this remarkable age of discovery that we have had the good fortune to live through, which is really amazing. So, see if I can move. There we go. So we begin really with the Mount Wilson 100-inch telescope, and we end with this image of the Webb on its way to the moon. and not to the moon, but to the L2 point, which is 1,000,000 kilometers beyond the moon. And so the question you may ask is, why do I stop at Webb? Webb is so amazing. Well, Webb will it's a long story, but it will make great discoveries. But really, the grand contours have been in place at the time the Webb is launched. And after all, it's 100 years. You have to draw the line somewhere. Okay. This is a quote from somebody that they made a movie about. And it is a profound and necessary truth that the deep things in science are not found because they are useful. They are found because it was possible to find them. And this is really the story of the astronomical century, because it happens that there was a revolution in physics and quantum mechanics. And from that revolution, we were able to understand the composition of the stars, the velocities of the stars, all of these things, because we understood how atoms and electrons work. One may ask, what is the value of pursuing fundamental science? Perhaps no value at all. But in fact, by understanding, by Rutherford's investigations of the atom, we have atomic energy, we have understandings of the deep understanding of how chemistry works, which then goes into advanced medicine and so forth. So fundamental science is understanding fundamentally how the world works, and then thereafter applying that knowledge to do amazing things. So we think about, as the astronomical century begins, let's look at what we do not know. We do not know why the sun shines. Many cultures, believe in a sun god. Japan today, its flag is the rising sun, Amaterasu, because the source of all life on Earth is the sun. But in 1920, we didn't know why it shines. We think that the sun and all the stars have the same composition as the Earth. We have no idea how old the Earth and the universe is. We have no idea about the scale of the universe. The solar system is unexplored. Recall the Scopes trial, right? Because there were people believed that the universe is really as old as it says in the Bible if you add up the generations, or around 3,000 years. We had not explored the universe in any wavelength other than visible light, the light your eyes can see. We don't know where the elements came from. We didn't even know there were elements. There may be life and civilizations on Mars or inside of the Earth or even inside of the sun. We had no idea that there are planets around other stars. The last scientist to seriously propose that planets orbit around other stars was Giordano Bruno. Not only did he not get any governmental funding, the government didn't just cut off his funding, they didn't cut off his head, they burned him at the stake, even better. So that shows where ignorance gets you. At the end of the astronomical century, we do know what the stars are made of. We understand the origin of stellar energy. We understand the life cycle of the stars and their link to the elements. We know the age of the Earth and the universe. We know the scale of the universe, the origin of galaxies. We've explored the solar system with space probes visiting all of the major bodies and asteroids and comets. We have walked on the moon and collected its rocks and returned them to Earth, along with robotic probes that have collected and returned lunar rocks to Earth. We have observed the universe with imagery across the electromagnetic spectrum, and telescopes the size of the Earth detect all forms and we've been able to detect all forms of light and also detect gravitational radiation and so forth, which is amazing, which shows that the very architecture of the universe, which is space-time, has waves that propagate at the speed of light, and therefore, forget it, Captain Kirk, there's no warp 9. We cannot go. Okay. So the major things that we do not know are big problems. Is there life elsewhere in the universe other than on the Earth? We so far have not found evidence for any, despite life, being found in every nook and cranny of the earth. And from the harsh fields of Antarctica to 2 miles below the ground in a gold mine, we can find life everywhere in the earth. But we do not know whether life even exists elsewhere in the solar system. And in fact, it is really unlikely that there is any life elsewhere in the solar system for reasons that I probably will not get to in this lecture. But briefly, if there were life on Mars, I think we would have found evidence of it. There's hope, maybe deep underground, maybe in certain volcanic areas. There is too much water in Europa and not enough carbon, and probably the energy sources necessary to produce life, forget it, probably not. Let's hope. Enceladus, maybe, but really it's a tough thing. And finally, we don't know the nature of most of the mass in the universe, which is the dark energy and the dark matter. We don't know the nature of those things. We know they are there, but we don't know the nature of them. For example, anyone in the room know what fundamental elementary particle is responsible for dark matter? Let me know if you find it and you can prove it. There is a party waiting for you in Sweden. Every year it happens. So we have, this is an incredible age, though we no longer need the sun god unless people ask me, and I guess, David, you'll have to cut me off because I will never get through in a reasonable time. I could go on and on, so give me a 5-minute warning and I will wrap up. But people ask me, what do you think about astrology? And astronomers always lose arguments when they fight with astrologers. First of all, there are no known forces that can affect us that emanate from the moon, planets, and sun, except for gravity, and gravity is not going to determine our life at birth. At least we don't have a theory about how that would work. But astrology does a lot of good, because when you spend money, you stimulate the economy. There's something called the multiplier. How many of you learned about the multiplier in Econ 1? Okay, so when you spend money, even stupidly and needlessly, you help stimulate the economy. In addition, in an era of very restricted healthcare, and it will only get worse, astrology offers a low-cost alternative to psychotherapy and psychology. Okay, so it does do a lot of good. I probably offended so many people at this point. Okay. So why did I make the boundary like this? Well, because on one end, at 1920, you have two great understandings, that Arthur Eddington understands that nuclear energy can be the only explanation for the origin of the sun's energy, that nuclear fusion, he doesn't exactly get it right, but he basically gets it right. And the other thing is, in 1921, we have this great debate in front of the National Academy of Sciences whether galaxies are inside the Milky Way or outside of the Milky Way. But then in 1921, Edwin Hubble points the 100-inch telescope toward the Andromeda Nebulae. He finds a Cepheid variable, and thanks to the very hard work of one Henrietta Leavitt, who establishes the period luminosity relationship, he is able to show that the Andromeda Galaxy is well outside of the Milky Way, is an island universe, and that the other galaxies are beyond. So these are really important things. Now, it's true that in 1930, Vesto Melvin, life or not Hubble, discovers the redshift in the expanding universe and so forth. But really, the proof that galaxies lie outside of the Milky Way, that's another very important thing. So these are the things that Arthur Eddington, I'm going to skip through this, and in fact, you can upload the slides or somewhere, but basically, he shows that the stars must fuse hydrogen into helium to get their energy. And Cecilia Payne, whose thesis was rejected by none other than Henry Norris Russell, for whom the American Astronomical Society still gives its top honor. He said it was a load of BS. Well, Cecilia Payne said, the sun must be composed primarily of hydrogen because I've done the atomic physics. She was absolutely right. The only problem was that she didn't get the Nobel Prize in Physics, which she richly deserved for that discovery. Arthur Eddington led a trip to the 1919 solar eclipse and to test Einstein's theory of relativity. He reported that he had measured the gravitational deflection. The consensus is that he probably did measure it. It's been debated for a long time. There's a book called Within a Shadow of a Doubt or something. The basic thing is that he probably did measure that deflection. So it was the first, at least it was the first effort at an experimental measurement of the new general theory of relativity, which made the amazing prediction that mass bends space-time and that light paths represent the straightest path in the universe that there can be, so they can be used to measure the way that mass bends space-time. So here is the detection of the Cepheid variable in M31. Now remember, we don't have that Cepheid period luminosity relationship without Henrietta Leavitt realizing, hey, there are all these pulsing stars in the Large Magellanic Cloud. They must all be at the same distance from us, so I can determine a relationship, between luminosity and period. The longer the period, the higher the luminosity, the bigger the bell, the lower the ring. Here's the 200-inch telescope. It was finished in 1948. A long time in the making. Hopefully we will see the 30-meter telescope finished. Here's the two 10-meter telescopes that I think David and I observed there so long ago. And in fact, I finally got a little more observing time to work on a dwarf galaxy in Andromeda there in October. And you can see the 10-meter mirror. And then this shows these are huge achievements that occurred during this period. So we have Mount Wilson at 100-inch. George Ellery Hale, who lived not far from here, dreamed of the 200-inch telescope, but he was also a great solar astronomer, and his real passion was the study of the magnetic fields of the sun and to understand how the sun works in detail, which is still one of the unappreciated fields of astronomy. Here we can see the installation of the Wide Field Planetary Camera 2 on the Hubble Space Telescope. You may recall that when the Hubble was first launched, horrifyingly, they could not reach focus, and they realized that despite being the most precise mirror ever made, it was made wrong with spherical aberration. In Naked Gun 1.5, the movie, they show all of these, terrible disasters like the Hindenburg, and up there was the Hubble. Well, the last laugh goes to the Hubble, which basically, actually, in fact, with Peak 2, measured the expansion of the universe with huge precision. The fight between Sandage and de Vaucouleurs was settled at 75 kilometers per second per megaparsec, and the expansion in between the two of them, because of the fact that the role of dark energy, discovered dark energy. The Webb will have a lot of work to do to beat what the Hubble did. And then I just saw this telescope. This telescope doesn't exist yet. It's a 39-meter telescope. But that is, the mirror would be a nice fit for the infield of Dodger Stadium. And in fact, maybe the Dodgers could consider, using the infield of Dodgers, fewer errors. Anyway, but in any case, or maybe they could use this telescope to discover how the bat works once again. No, they seem to have lost that. Okay, so anyway, I saw this telescope under construction. And it's just amazing. It's being built by the dome and so on. Is being built by a company that builds soccer stadiums that have movable roofs, an appropriate choice because it's about the size of a soccer stadium. And I've actually had the honor of going to see this telescope. I should have included some slides showing it under construction, but this is an amazing thing. It's absolutely amazing. Here, in 1982, the Voyager spacecraft, which has now exited the solar system, and is 167 times the Earth-Sun distance away, and yet a tiny fraction, less than 1% of the way to the nearest star. So it's far away, it's moving fast, but but this shows the gallery. So in 1950, we had images of Mars from peak to midi. This is the best image we could get of Mars. Then now here we have Venus has been revealed as a desolate, boiling lava field. And by the way, Carl Sagan, who was a great publicist but also a great scientist, pioneered, and he made two extraordinary predictions. He said global warming would turn Venus into a hellscape. When I was a kid, I actually had books showing, Venus might have oceans and maybe dinosaurs or something. Well, any dinosaurs here are really charbroiled. But the interesting thing about Venus, which is why it's unfortunate that some missions to Venus are canceled, is that we talk about a period of habitability of planets, which is interesting. The reason we are excited about Mars is because Mars had a period of habitability of roughly 500 million to 1 billion years, during which time perhaps the first steps of life, or even perhaps single-cell organisms, might have arisen. And so, which is exciting. Venus had a period of habitability possibly as long because it's closer to the sun, so therefore its greenhouse, it went into the moist greenhouse phase, that is a runaway, but it may have had 2 to 3 billion years of habitability. So there might have been more complex life that evolved on Venus and then was charbroiled. We have discovered some amazing things on Venus. It's one thing that was remarkable. It says coal is a wonderful source of clean energy. That was written in Venusian that we found. Ban solar energy. So anyway, okay, yeah. So this is an amazing thing. About 50 years ago, we had the first GM built back in the day when they were very successful at building, well, they still are successful at building cars. This is an electric car. It has silver iodide battery, which is amazing.
The best place to order restaurant catering for your workplace.
Let's see.
Find anything you need in just a few clicks. Order now at easycatering.com.
Okay. Yeah. Something happened. Maybe some larger forces didn't like my jokes about solar and coal and so on. Let's see if we get the full screen here again. Okay, so this is even better. It'll let me know how long I've talked. And this shows the Viking 1 landing site. And again, when I was a kid in 1976, I thought, there had been these images. I was so depressed when Mariner 4 flew by Mars and returned images showing desolate craters. But then further missions showed these, signs of flowing water, and Viking orbiter showed really interesting river valleys and other, so there's definitely evidence of flowing water, which there still is. But I thought, as a kid, well, maybe when Viking lands, it'll return pictures of cacti. You never know. It's a desert planet. Well, this is landing of two sophisticated biological laboratories on Mars successfully, is an achievement equal to the landing on the moon that very few people know about or remember. It's July 4th, 1976, celebrating our bicentenary with this great achievement of landing these biological laboratories on Mars. Now, they made a delicious organic soup, and the 4 experiments were supposed to detect possible life that might arise or be eating this delicious food that we were offering them. There was one experiment, the labeled release experiment, that produced some interesting results, but because, for a long story, because the soil has a lot of perchlorates, almost certainly there's nothing alive, at least not at those 2 sites. And since then, while we have sent very sophisticated rovers, none of these are designed to search for life or biological processes themselves. The one rover that was designed to do that by the European Space Agency sadly did not survive the landing attempt. So we have also, what we have seen, we've seen meteorites on Mars, but we've not seen fossils. I had wanted in the movie The Martian to have him be digging in there trying to find soil to grow his potatoes and then dig up some fossil clams. But let's be realistic, okay? When I teach in Astro 5, which is the life in the universe, that the Earth has existed for 4.6 billion years, but only 600 million years ago did life have anything more than one cell. And the biggest event was the cyanobacteria 2.5 billion years ago that created the first oxygen. So we did not have multicellular organisms for 90% of the history of Earth. So if we find life on another world, the likelihood is that it will be single-cell organisms.
Towards the
Boy,
plane.
they really, really don't like what I'm talking about here. You know, maybe. Okay. Okay. Oh, well, I need to move. I know I can do it this way. I won't press any buttons on the keyboard. Okay. So this, by the way, is fun. This is an imager from Surveyor, 1967. And then where did David Hockney get his inspiration to do something like that? This is not a joke. He was inspired by these images that NASA put together because they didn't have a high bandwidth system of delivering the data. So each one of these sub-pictures represented quite a slow delivery of data, and then they pasted them together to make these panoramas. And he thought, this is cool. I can do this. Here, I think that this painting, if you sold this painting, it would actually fund a decent mission to go to Venus. But of course, the Getty will never sell it, but I think it would hammer well in excess of probably 100 million. This is probably be the most expensive photograph ever sold at auction. But we don't want that to happen. This is a beautiful image. So this is Pluto from New Horizons. So I was talking about, we discovered this is such a beautiful image. You can see the atmosphere of Pluto. You can see mountains that are made of water ice. You can see an ocean of frozen nitrogen, and the heat source for doing all of this is unknown at present. It's probably thorium decay, but what else can it be, right? So, and this is Arakoth, which is the most distant object. It is part of the Kuiper Belt, and this is a tiny thing, about 10 miles across, and this is looks for all the world like what we call a planetesimal, in which the solar system formed. So this was done by the New Horizons mission, and this was in 2019, just before the last New Year's Eve before the pandemic. I was excited to see what Arakoth would look like. And then this is an amazing image. This is taken by the Voyager while it still had its camera working. It's turned off the camera now. And then this is the solar system family portrait. And it's superimposed on the solar system here. And then we zoom in here, and there's this little tiny blue dot, the pale blue dot Carl Sagan refers to. And Sagan said that all of the kings that ever lived, all of the battles and the empires and so on took place on this tiny blue dot, this piece of rock orbiting the sun. It is insignificant in its mass, location in the galaxy, but it is very significant. I mean, we are insignificant as well in the fact that we are not made of what most of the universe is made of. Most of the universe is made of dark matter, dark energy. We are made of normal matter. The elements that we are made of are produced inside of supernovae. And in fact, the whole life cycles of stars was another achievement that was uncovered during the Astronomical Century. In the landmark paper by Burbage, Fowler, and Hoyle, 1957, the origin of the elements, the light elements, most of life's light elements, oxygen, carbon, nitrogen, and so forth, are produced in the deaths of massive stars that are more than 10 times the mass of the sun. The iron is produced in supernova explosions of white dwarf stars that are the remnants of the evolution of stars like the sun, the full process of type 1a supernovae, which, by the way, are the fundamental distance scale that we use to measure the scale of the universe and discover dark energy. That mechanism is still not fully described, so that's an unsolved problem. Here we have a remarkable image. Planets orbiting a star. This is HR 8799 obtained with CAC 20 AU is 20 Earth-Sun distances. Jupiter is at 5 astronomical units, Saturn at 9 AU. And you can actually see these bodies orbiting this star. The star is blacked out. The little speckles and things that you see here are due to a very sophisticated device called coronagraph that suppresses the star that would ordinarily be so bright we couldn't see these planets. Now the trick here is that this is actually a young system, only about 3 million years old, and the planets are still extremely hot. They're about 3,000 Kelvin. So we're able to see them because they're glowing in thermal light. The Earth, of course, is 300 Kelvin and doesn't glow. If it did, if Earth was 3,000 Kelvin, it would be very uncomfortable here. But this is a young planetary system, and all of these planets here are multiples of the mass of Jupiter. So we're not, what's remarkable is this is a solar system, but it's not a solar system like ours, and we don't see any planets like the Earth. Want to see something like this with Earth-like planets orbiting a sun-like star? No problem. For the price of the override request for certain budget things connected with, border security, $60 billion, for that price tag, we can definitely build the requisite 16-meter telescope in space that would give us an image like this for all the stars within 30 parsecs or 100 light years of the sun. So it would cost about $50 to $60 billion to get that. That is how much more difficult it is, because trying to see a planet by reflected light, as you probably have learned from other speakers today, is the equivalent of trying to study a moth flying in a searchlight with a telescope located in Los Angeles and the moth flying in the searchlight in New York. It's really, really hard. So this is possible because the planets are still hot because it's a young star and they're still cooling from their heat formation. Okay. So this is an image I gave this talk in Sweden about a year ago at Lund, where I received an honorary degree from Lund University, which is very moving. And I wanted to show Knut Lundmark's achievement. He was the first person to do he actually used actual star counts to make this painting of the Milky Way as it should appear based on the number of stars. So he also showed the big clouds of dark clouds of reddening. And by the way, an achievement that occurred here in California was that Robert Trumpler actually determined the cause of these dark clouds here is dust produced in stars in between us and the Milky Way. So they discovered interstellar reddening. So now this map here, another European achievement. The Europeans are going to be leading in astronomy in the future, is from the Gaia satellite, which has mapped the positions and velocities and magnitudes of 1 billion stars, more than 1 billion stars. So it's a huge achievement. And so I showed this, and this is really, most people, how many of you have ever heard of the Gaia satellite? Okay. That's good. I'm impressed, because really, in fact, it's been used to do some amazing discoveries. About a year ago, a 33 solar mass black hole was discovered that is not making any other kind of emission, and then except what it is doing is it's affecting the gravity of nearby stars. And so it was discovered from the Gaia satellite observations, detailed observations of nearby star motions. And in fact, when the next data release comes, we expect to see the discovery of exoplanets that are revealed by how these planets tug on their stars as they orbit around them. So that stay tuned. Gaia has more amazing things to give us. Not far from here at the California Institute of Technology, Martin Schmidt and many astronomers, Alan Sandage was competing from Carnegie Institution of Washington at the 200-inch telescope that was built and designed by Carnegie Institution and Caltech. And there were these radio stars that were discovered that were very strange. Nobody knew what they were. And when you tried to take a spectrum, the lines didn't make sense. Jesse Greenstein thought they might be some strange kind of white dwarf with very high magnetic field or surface gravity. Nobody knew precisely what they were. And then Martin Schmidt fortuitously got the spectrum, and he recognized the lines of the hydrogen-Balmer series, except the redshift, the distance, which is the redshift, was spectacular. Nothing had been seen like this. I forget exactly I should know the redshift of 3C273, but it was in excess of 0.5. And so when you went to do the calculation, how bright is this object? It was insane. There was no source that could power this. You observe objects like this today with radio telescopes, and you see these vast blobs of synchrotron radiation, the radiation that electrons make when they spiral in magnetic fields, and jets pointing back to a black hole. The source of that energy that makes 3C273 so bright is a black hole of billions of solar masses. And what happens is that when material falls into the black hole, much of its energy is converted to some fraction of mass times the speed of light squared. Remember that famous equation, E equals mc squared? Well, that's the origin. The gravitational energy that turns potential energy into kinetic energy, that's what makes quasars shine and are so luminous. These spectra here illustrate perhaps the greatest single discovery of the Keck telescopes. It was when the Keck telescopes had their first light, many astronomers predicted that we would be lucky to see normal galaxies that were maybe 500 million light years away. We really didn't know, maybe a couple billion at most, but normal galaxies like the Milky Way, we would probably never see them at great redshifts like we could see the quasars. Charles Steidel of Caltech came up with a method of discovering galaxies whose light was blocked by hydrogen at 912 angstroms, because that is the energy that tears the electron away from hydrogen, so that no light gets past that. And he found this class of galaxies, and sure enough, they were at a redshift of 3.5 for a look-back time of over 12 billion years, only a billion years, about 1.5 billion years after the Big Bang. So we suddenly expanded our study of the evolution of normal galaxies. Late in this astronomical century, we found normal galaxies like the Milky Way in the state of formation, which is amazing. You've probably seen these images here taken by the Event Horizon Telescope. This is an image of the galaxy Messier, of the black hole in the galaxy Messier 87. And the little round thing, I believe, is the size of the black hole's event horizon. And so we've actually been able to image the gas behind the black hole as well, and being bent by the bending of space-time by the black hole being visible to us. And we have done this for the center of our Milky Way and for the center of Messier 87. And this I mentioned very early in the talk about how gravitational radiation was detected. Now we're going to propose to close down our research on gravitational radiation as America steps back from science and truth, which is very sad. Hopefully there will be some way to stop that from happening. But what you see here are two events where two black holes about 10, 20, and 30 solar masses merge, and there is something called the ring down here. So you see them making this, getting closer and closer, and then they merge into one black hole. This is about 1 billion light years away. Two different telescopes, located one in Hanford, Washington, the other in Louisiana, both measured this event in gravitational radiation. The Earth, the distance between the two telescopes is modified slightly by this ripple in space-time. And we've actually been able to show that these ripples in space-time move at the speed of light, which is amazing. And this plot here, this is really hard to explain. This is a plot of the size, the number of patches of microwave background versus size. So I should mention that we can actually detect the hot Big Bang. We can actually look back to a time when the universe, the entire universe, everything, was 3,000 Kelvin. Further than that, we cannot look back because we cannot look past ionized gas, just like you can't look into a cloud. But this shows that the universe was once very, very hot and dense. What these ripples show us here is how the dark matter, the dark energy, and the normal matter were interacting, and thus give us the whole geometry of the universe. This was determined from two missions, the Wilkinson Microwave Anisotropy Probe and the Planck mission, and they really give us an amazing picture in detail of the universe, its evolution, its expansion, and the impact of dark matter and dark energy. And this plot here, another great contribution of this astronomical century, is the plot of star formation history of the universe. So when you go to redshift of 8, the look back time is nearly 13 billion years. So we're looking back almost to the very first galaxies to form. Now the Webb is pushing back farther, pushing closer to the Big Bang itself. We've seen galaxies with the Webb that formed only about 300 million years after the Big Bang. But this was all mapped out with Hubble and Keck, and basically shows that the universe began with a very small amount of star formation and galaxy formation. And then 2 billion years after the Big Bang, it burgeoned into something called the Bright Ages and has been declining ever since as the hydrogen gas is consumed. So there's less star formation now. We're almost back to where we were at the beginning in terms of star formation. Over 50 years ago, this amazing image of the Earth suspended in the blackness of space. Now, Neil Tyson likes to say that the universe wants to kill us. The universe does not have intent. The universe just does not, in most locations, support life. The image of this Earth was so shocking to see the Earth and this everything we live on suspended in this hostile blackness that it led to the creation of the Environmental Protection Agency, which today, sadly, is being dismantled. But the truth of this image remains that of all of the amazing things that we have discovered in the universe, we have not discovered another place where life, which is, we've discovered 5,000 exoplanet candidates. We have not discovered a single one where it is highly likely, well, there may be people in the field who disagree with me, but for complicated reasons, I would say the gold standard is an Earth-like planet around a Sun-like star with detection of ozone, oxygen, and the atmosphere, yada, yada, yada. We haven't discovered that. The problem with the planets that are in the habitable zones of brown dwarfs and M dwarfs is that they are likely tidally locked, which is not going to be comfortable for life forms. But who knows? Life is creative. The point is that the real fundamental thing is our agency, our intelligence, and the free will that we have to decide whether to save our amazing achievements and our amazing planet and to honor this great period in our history, largely with American leadership, especially when it comes to landing on the moon and the exploration of the universe, but it was a total world achievement to discover the universe and understand deeply the universe in the astronomical century. Thank
We have time for a few questions here. Yeah. Is there another level poorly where 800 million years in the future and we're just having the wrong time?
Well, when we look at light, light is bringing us the latest news, but light travels at a finite speed. But when we talk about searching for life in around other stars and so on, we are talking about essentially looking at a field of regard that is maybe 100 light years in volume, just realistically. We in terms of the detailed study of, now, I could qualify this and say, well, maybe and possibly, but basically, the even if you look out 1,000 light years, it's just an instant. So the impact, you're not looking a billion years, you're not receiving information a billion years in the past. We can't ever hope to look at galaxies, 500 million light years away and hope to see dinosaurs or whatever, because forget it. They can't even resolve individual stars except if they're supernovae. So.
Any questions for me? I have one for you, Mike. What are you most excited about in terms of the next telescopes? You mentioned the 30-meter telescope, the ELT. What capabilities do they bring that you're excited to use?
Well, the European Extremely Large Telescope, if it works as hoped with fully adaptive optics, will have a resolution that will be nearly 10 times that of the Webb, or 8 times that of the Webb. And so in terms of my study of the subject of stellar populations, I'd be very interested to measure the formation ages of the nearest giant elliptical galaxy, which is Centaurus A, NGC 1528. I'd like to also actually measure the compositions of its stars and see if they experienced a different history of compositional enrichment. But I can tell you that the people in Europe are most excited about searching. They think that the EELT will be the first telescope to have a shot at searching for Earth-like planets around sun-like stars. They want to do that. And then also it will be able, it won't, the thing about Webb is the mirror is extremely cold. So it's 1,000,000 times more sensitive, or 10 million times more sensitive than anything on Earth, just because the mirror is at 40 Kelvin. Okay. Secondly, it is sensitive from 1 to 5 microns. The atmosphere has got lots of water and other features, CO and CO2 and so on, all sorts of problems in between that wavelength range. So it's very difficult to study high redshift galaxies whose light is moved into that wavelength range. But with Webb, you just bing, 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 here are all the lines: neon, carbon, nitrogen, oxygen. You can see the buildup of elements in galaxies. So I'm still excited to see what happens with the buildup of elements in galaxies in the early universe. Where did supermassive black holes come from? Okay.
Well, and then just a last comment, and you and I can talk about this later. You saw the recent LIGO merger that was like 100 solar masses and 100 and something. So it's another intermediate mass black hole merger, but the biggest one yet. It was just announced
actually,
a little bit ago.
intermediate mass black hole, you've got to be well over, say, 1,000 solar masses. But 100 and 150 is pretty big.
This is getting
The
there.
problem is that the LIGO doesn't have, it's
No.
not sensitive to more, you need to have the LISA array to
Yes,
see those.
exactly. So this gets us to the point
Yeah.
that they were pushing the boundaries
Yeah.
to get that result. And LISA's another bigger, better gravitational wave observatory that's on the chopping block. So,
Well, actually, the U.S. participation in LISA is on the chopping
yeah,
block.
yeah. So
And then,
it's-
but you know, that's, yeah, they basically, I don't know why there is this anti-science thing. You know, Vannevar Bush told Eisenhower that science is the endless frontier and the key to U.S. national security is to build a strength in science. I don't know where we forgot about that.
anyway,
It's still
let's
true.
Let's thank our speaker again.
Thank
so
you.
much.